So, our very last talk of the conference is Sergiy Verstyuk. So this continues a tradition of wrapping up the conference with one of our totally awesome big data postdocs. He's here as a postdoc at the CMSA after completing his PhD at Chicago, and prior to that, a master's in econometric methods and mathematical economics at LSE. He worked in the global markets team at Goldman Sachs, was also a research fellow of the Institute for Economic Research and Policy Consulting. I understand that he was also a champion soccer and basketball player. Is this accurate?
That is accurate.
That is accurate. And on a personal note, I should add, as one of the people who runs the big data and social science programs at the center, I was involved in the process of bringing him here. And suffice it to say that you're flipping through sort of stacks of applications, and then you come across his, and your jaw hits the floor. One of the easiest reads ever, as measured by the material was sufficiently complex that it was actually quite difficult to read, but by the time we'd managed to navigate and understand it, it was obvious we wanted him here. So we're very, very glad to have Sergiy here and to have him wrapping up the conference with modeling multivariate time series in economics, autoregressions versus recurrent neural networks. Let's welcome him.
Thank you, Scott. Okay. I will talk about what modern machine learning and specifically deep learning methods can bring into economics. Just to preview the results, I will show that they are good at forecasting and that they help us disentangle some of the economic relationships between, say, policy variables and economic performance variables that we are interested in. Just to get this out of the way, this is the most boring part of the presentation, the data. So these kind of methods I'm using require a lot of data. In economics, we have very little data. It's our consistent, high-quality data really starts only after Second World War. Moreover, a lot of the data we're using are collected at quarterly frequency. So what I'm doing is I'm interpolating the quarterly frequency data into monthly frequency, and for that what I'm using is a version of state space model, which I wasn't the inventor, but this is more or less an accepted way of doing things. And the benefit of doing it is that it uses monthly frequency variables such as industrial production, say, to inform the inter-quarter ends changes in the, say, GDP. So these are the variables I am looking at: the real GDP, the GDP deflator, which is a price level, the commodity price level, which is includes goods such as oil or metals. Fed funds level is interest rate that the Federal Reserve, the monetary authority of the United States, is targeting, and it's a key instrument of the monetary policy. And I'm also looking at the total and non-borrowed reserves. These are the funds that commercial banks are holding at the Federal Reserve, and they are also a useful measure of monetary policy. In fact, it was proposed to be used sometimes in the end of 80s or early 90s, and back then, as you can see on the graph, actually they didn't move too much, and they became really useful after financial crisis, because after the federal funds rate has hit the zero lower bound, actually the quantitative easing started. And that's how one way to look at its manifestation is this reserves measure. So what I'm really using is a transformed version of these variables. So that's the data issue. The rest will hopefully be more entertaining. So the The first method I'm looking at is vector autoregression. This is a very classical statistical method, popular in economics. It's all over the textbooks. It has been developed for a while. There are a lot of different versions of it and subversions. I'm using a plain vanilla one so that it's the most simple and the most transparent. The way it works is that you have a variable or a vector of variables at time t, and you're using past values of this same variable to try to explain the dynamics in its behavior. And that dynamics is guided by coefficients A, which are parameters to be estimated. The method I'm really interested in is artificial neural networks. So there are a huge range of different architectures that people have developed. Just to give you a quick taste, so the simplest one is a feed-forward architecture where the inputs come, these yellow cells, then in green cells, this is a hidden layer where those inputs are transformed, and then the output, the red cells, is produced. Some of the versions of neural networks have extra cells which are doing some more sophisticated transformations. For example, convolutional network uses convolution cells, and it's useful for image processing. The recurrent networks, it has cells which feed into itself, and this architecture is useful for tracking sequential variables, for example, video, or more simply, just language or music. What the model I am actually using is long short-term memory. This is a version of recurrent network, and I don't want to spend too much time on the mathematical details, but the idea here is that you have some inputs into the system. Here it's a variable x. And then you want to forecast the value of that variable at the next period, so from t to t plus 1. Along the way, you construct some variables that help the network constructs some variables, state variables that help to track the dynamics of the variable of interest. So in all the recurrent networks, the key of such variable is h, the hidden state variable. In long short-term memory, there is an extra variable which is memory state. So the way the network works is that it gets an input as x. It also gets an input of h from the previous layer. It also gets an input of c, the memory, from itself, from the previous iteration, and then it produces x or h if it's not the last layer for the next layer, and then it produces c updates its memory state for the next iteration. As you can see from the reference 97, this has been developed a while ago, but only recently we learned how to really use it productively. Okay, so the data I have is kind of short, and even by multiplying it effectively by 3, by doing this monthly interpolation, it's still less than 700 observations that I can use for estimation and training, because I also need to leave something for testing after the exercise. So for autoregression, what I'm doing is that I'm splitting the sample into estimation sample and testing sample. The testing sample I do not touch. For the estimation sample, that's the usual OLS that we are all familiar with. For the neural network, what I'm doing is I'm also splitting the estimation sample into two parts. One is the training sample, a larger part, which I'm actually using to modify the parameters in my network in order to feed the data. And then I have a validation set, which I'm using to periodically cross-check how is my network doing in forecasting. And if I see that the forecasting performance starts to deteriorate, it means that the network has learned all the structural interactions underlying the systems that are important, and it starts to memorize the data. Yes, please.
For the recurrent neural network, do you have a lag concept or use all the time?
It's effectively, look, actually, it's very similar to vector autoregression in this sense. Technically, you have a lag here, but you can unroll it, right? You can unroll it into the past as far as you want, just substituting back into the equation. You can do exactly the same with neural network. Technically, it uses only lag 1 from x to xt plus 1, but you can unroll it as far back as you want. And in fact, and that's probably why you ask.
But that's not quite the same.
Exactly, yeah, of course. It's not quite the same, yes. So they are not.
L equals to 1 is sort of more parsimony than L equals 3, right? Or L equals to
I see, of course. So there are variations, so it's not exactly one-to-one.
No. I'm just wondering what, when you are doing the training, do you restrict the recurrent neural network to, in other words, what are the exits you are using?
Yeah, so look, probably what you really mean is how far back I go when I'm computing my gradient in back propagation, which is the chief method of training my network. Because in principle, I can compute my gradient all the way to my first data point, but that's very expensive. So in practice, what people do is that they compute the gradient only several steps. So in my case, I'm using 24 steps. Okay. So yeah, the network, when the network stops really learning and starts to blindly memorizing the data, then that's it. I call it stop, and we are done. The architecture I'm using is 3 hidden layers, 200 nodes in the first, 300 in the second, 200 in the third. Sometimes people use this bottleneck infrastructure.
In this case, what's your y, what's your x? What have you mentioned?
In my neural network case, it's exactly the same variable as here. GDP, deflation, commodity prices, Fed funds, total reserves. So today,
you want to predict
the day in 1 month's time, then I take it in 1 month's time and predict in 2 months' time, and so on.
You access the past 24 days of the 5 values?
Well, I start from the beginning and I end at the end.
Sorry?
I start at the very beginning and I end at the very end, and just doing step by step. So at the end, I cover all the data. Are you asking how far in the future I'm trying to forecast?
No. For example, in this model, I only need to look at the past 3 days. If I'm predicting, if I already trained my model, right? For example, L equals to 3. For this model, I'm only looking at the past 3 periods.
Mm-hmm.
That's it.
But
You're
that's
not looking beyond that.
well,
It's different from
I'm-
training and predicting. So I'm trying to clarify. I'm not questioning anything. I'm actually just trying to clarify for my
I
understanding.
understand. So look, for estimation, I use if you're
For your model, for recurrent, I'm not talking about training yet. I'm just asking, what is your particular recurrent neural network model for, say, for plugging in like this? this. For this one, I'm very absolutely clear. I'm only looking at past L period and plug in those values.
Sorry, look, I'm not sure I understand the question. Let's talk about it after that.
If you told me this equation,
Yeah, so is the question whether L is, L fixed with a given value, or sort of L is just always back to take 0 each day?
this one I'm very clear. So this theoretically, suppose God given me L, give me all the coefficients and plug in, I know exactly what I'm doing. That's, I assume, no whether it's true or not, it's a different question.
Okay.
What I'm asking is the equivalent question for recurrent neural network. What is that assuming in terms of your sort of oracle? What's your oracle equation? Yeah, what's your oracle equation? So suppose you know all the, without training, suppose you have perfect training, you have all the perfect ways. What are you computing from?
Okay, so say if I'm asked to forecast the variable in 1 month's time, if you
I'm just asking what is your x?
I understand. So say if your question is how do I forecast GDP in 1 month's time, then next month, what information do I need for that once the network is already trained? I need this month's GDP. Okay, is that what you were asking?
That's equivalent to the L is what in the previous.
It's not, well, these models are not equivalent. So nothing is equivalent here.
But for the L, how large L?
Analogous L1.
L equals 1.
Yes.
So in other words, your equivalent information, not equivalent model.
But I just want to repeat that here, this L is also, it has the purpose of, it serves the purpose of just adding extra coefficients A, but in reality, my model depends on all the history here.
Well, that's what you're training. That's
Yeah.
trying to make this example.
So yes, if you want to hear what a similar notion as L in my case is L1. Okay, so these are the details. Now, these are just diagnostic plots to see what's happening in the training sample, whether I fitted the data well. It looks like it does a good job. The blue are the actual numbers. The green is the VAR, the red is the neural network. You can see that neural network doesn't do great in the very last end of the data, and this is the sample that we use for validation. So the neural network barely sees that data, so it's all right that it doesn't capture it correctly. Now, there are two aims I'm interested in here, and two exercises I will do. First is forecasting. You may be interested in forecasting as a private investor. You may be interested in it as a, say, a planner of a budget for public budget or budget for a company. So you want to use a model like this to forecast the GDP, say, in a year's time. When I use VAR versus neural network, in the estimation sample, the VAR outperforms. Mean squared errors are smaller, and this is as expected because that's what VAR was designed for. Remember that I'm stopping my neural network from learning early so that it does well in forecasting. So if I let it learn further, it would have reached very low mean squared errors as well, and given that it's nonlinear, probably even lower than VARs, but we don't want to do that because we are interested in forecasting over the true testing sample. And in the true testing sample, actually, the neural network does better. The mean squared errors are smaller. The scales are large because I end up aggregating the raw numbers, but actually the training itself is happening in this on standardized variables. so don't worry about that. These are the plots that show predictions on the validation set, so we don't care that much about it. Now, this is the prediction over the testing set. So this is where, just to clarify, so the models haven't seen those data. I trained them on very different data, and now I tell them, okay, so here is the period I'm interested in, here are the inputs that you need to produce those forecasts, and let's see what you produce. And you may be a little bit disappointed that neither of the models capture all the high frequency movements, but this is expected because most of the high frequency movements are noise. Say number of working days can differ in January of different year. These models do not have enough history to understand this kind of relationship unless I tell it explicitly. Or the other variables affect the economy beyond the 5 variables I include in the system. The important part here is to capture the conditional mean, which ends up being this flattish curve that you see. And given that MSE of the neural network is smaller, so it gets the conditional mean better, in fact, you see that the differences in conditional mean are not that huge. But remember that we are looking at the monthly frequency, and those numbers accumulate. So for example, if you are forecasting GDP, and if you are a professional forecaster forecasting GDP at the end of the year and over 2 months, over 12 months, say if you are more accurate than your peer by 0.05 percentage point, it accumulates to more than a half percentage point by the end of the year. So if you look at the spread of professional forecasters, usually you would see that half a percentage point in the right direction would, in most cases, will move you really from the average forecaster to one of the top ones. Another thing that you may be worried about is that how come the MSE for neural network is smaller, but actually for fed funds rate, actually there are some of these strange red spikes that we see that are clearly off from the different from the blue lines that are the real data. The reality why these spikes do not affect the MSE too much, because the fed funds is a relatively volatile variable here. So when I'm doing the training and when I'm doing model comparison, I'm looking at the standardized variables as it should be. That's the kosher way of doing it. So at the end, those red spikes, when weighted correctly, they are not as huge as they look on pictures. This is a result of a second exercise. So now what I'm trying to do is trying to see if I give an input to a model and ask it to simulate the dynamics of the system in the future. How will different value of the input modify the dynamics? For example, if I'm a policymaker, Federal Reserve, I'm interested what the change in monetary policy stance, say an increase of Fed funds rate, will do to the GDP, to inflation, and so on. Again, just to remind, the green line is the VAR, the red line is the neural network, and the blue lines are just the means over the sample. So for GDP, an increase in the federal funds rate, which makes the financial policy more restrictive, leads to, according to VAR, to an increase in GDP and then to a decrease, and at the end it levels off at the mean. This is a little bit counterintuitive. Usually we think of a more restrictive monetary policy as depressing output rather than producing a spike. The neural network does actually capture the fact that the GDP decreases a little bit. and then levels off again at the mean. The deflation, the price level, is more interesting. Here, the models clearly diverge. An increase in the federal funds rate increases the price level, according to VAR, which makes no sense. All the economic knowledge we have, however limited it is, says that shouldn't be happening. And in fact, this is a well-known disadvantage of VAR. This has been called price puzzle, and it is responsible for a whole new literature in economics, which is development of so-called structural VARs, which try to import some of the theoretical restrictions we have from economic theory into statistical models, trying to constrain them in a way that would make them behave according to what our theories want them to behave like. However, when we ask the same question in neural network, it has no problem figuring out the correct relationship. The increase in federal funds rate decreases the price level. In fact, this is the biggest difference between these two methods. The commodity prices, an increase in federal funds rate leads to, in both cases, leads to a decrease in the commodity prices, and this is as expected because an increase in federal funds rate makes the US dollar more valuable, and so commodities are, the price of commodities is measured in US dollars, so if US dollars becomes more valuable, then the price of oil or metal becomes lower. That's normal. And then there is the dynamics for the federal funds rate itself, which is slow reversion to the mean. And then the non-borrowed reserves, the second indicator of monetary policy, an increase in federal funds rate reduces the amount of reserves held with the Federal Reserve by commercial banks, and this makes sense because the higher is the federal funds rate, the higher are the opportunity costs of holding those reserves unused in the bank's business. So that's reasonable, but both methods capture this effect. So this is the second exercise, and just to summarize, I ran two methods. One very classical, it's very plain vanilla form versus artificial neural network. And even though we have very little data, but that's the reality we have to live with. And even despite these limitations of the data, we actually managed to get some interesting results. And in fact, the first result is that, as expected, the artificial neural network does better in prediction. A second result is not something I expected to see, actually, that it also guesses the interrelationship between variables, and what it guesses about this interrelationship looks reasonable. And remember that I didn't impose any economic knowledge into it. I didn't import any theoretical restrictions. It learned it itself. Just as a last comment, probably the reason why the VAR linear model captures that effect incorrectly is because usually high interest rates are associated with high inflation. So when a VAR sees that the interest rate increases, it thinks that probably inflation should increase as well. What happens with the neural network is that it manages to not to confuse correlation with causation, and it realizes that yes, if inflation is high, then it will also it is likely that the Federal Reserve will increase interest rate. However, if the Federal Reserve increases interest first, then the second move is actually a decline in inflation rather than an increase, which is this correlation versus causation link and its disentanglement is, to me, is an interesting result. Any questions? Yes, please. Sorry, can you please repeat? I barely heard.
No, I was wondering, using the idea of transfer learning to expand the data set. So if you would train or assemble a data that for economies that resemble each other, so for example, you would train a model on British economy or German and then forecast on US markets, how does that sort of expand the data and the performance of the models?
Look, that's something people use for, not for neural network, but they use for more traditional statistical methods. And this is a useful exercise, of course. But the hardship of this exercise comes from the fact that economies are different. And so when you use data from other economies, usually it would amount to the need to increase the number of parameters in the model you estimate, and hopefully that increase in the number of parameters, if especially you apply some theoretical restriction, is not that huge and justifies importing of data. But for that you would need to use normally you would need to use some theoretical restrictions, which is kind of defeats the whole purpose of the exercise, at least in a non-structural task I'm pursuing.
So I think when you are forecasting in the future, the VAR models can be used to construct like confidence intervals. So if you forecast, let's say, way ahead in the future, your intervals are wider. So can you say anything about the uncertainty of your prediction when you are using recurrent neural networks?
Yes, of course, and the way you can use that you can evaluate the uncertainty about that forecast is to, for example, you can in principle, the network that I'm using is in some way stochastic, because when I was training it, the training itself is partly a result of stochastic search. So nobody prevents you from doing exactly the same exercise, but obtaining slightly different network and trying to forecast with that network. And then if you aggregate a bunch of those forecasts, then at the end you don't have a point forecast, but a spread of forecasts that can help you evaluate the uncertainty around those data points that you are looking at. Okay, then.
Wait, I have a question. Sorry, were you about to?
Yeah, so as I'm leaving the floor, just wanted to thank the organizers for making this conference happen.
Awesome. Thank you. Let's thank Sergiy again.